Hello, friend. Welcome. My name is Derek Carter, and in this video, we're going to continue our discussion of processes in the x86 operating system. So we're going to take a deep dive. So we're doing two things in here. We'll talk a little bit more details, insertion details of how processes are implemented in x86 and what they do. So a little bit more about the details of what the process abstraction does in an operating system. And then we're going to kind of step through the boot process of the x86 operating system from the very first assembly language code that the boot ROM will jump to the place where the initial process, the process called init, the first user space process is created and started running by the operating system. Okay, so while we do this, you'll learn a lot more about the details about how processes actually work in an operating system like this and what they do. All right, if you're ready, let's go ahead and get started then. Okay, so we've probably covered all these points before, but the unit of isolation in x86, like in all other Unix-like operating systems, is a process. Okay, so a process is an abstraction. It's a mechanism in order to provide a simplified way for user applications to be built and use computing hardware. That's what we mean by an abstraction. So the process is kind of, I don't know, you can make an argument that's the most important abstraction of the ones that we might think of. It's the one that prevents one process from reading or writing another's memory, messing with another CPU or file descriptors or anything like that. So the process abstraction is how we set up isolation and protection mechanisms between the various entities that we want to be running simultaneously and using the hardware successfully and keep them from interfering with one another. Right, so it's very important that it sets up this isolation so that they can't, either accidentally or on purpose, mess with one another. Not to mention, it also, this isolation also goes for preventing processes from messing with the operating system kernel itself, right? So, all the same things. So by setting up virtual address space and these other things, we want to make it, it's not impossible, but we want to make it so that it shouldn't legally be possible for a process to be able to change or look at the kernel memory or the kernel code in any way. We've run across these mechanisms. So these hardware mechanisms need to be provided by the CPU architecture in order to implement a modern operating system. So you have to have at least some sort of a mode between a less and a more privileged mode. So user mode, supervisor mode flag. When you're in supervisor mode, like we've talked about before, only certain things can only be done when you're in supervisor mode. There's certain instructions that can only be run. Certain registers can only be set when you're in supervisor mode. An important one is the page table register. So there's one register that's going to point to the place in memory where the page table is that's going to be used by the CPU whenever it has a memory address that it needs to dereference. Okay. So that's the beginning of setting up address spaces. The operating system has to set up the page tables when in supervisor mode, and there's going to be a particular register that we'll see what that register actually is in this video here that's set to the location where the page table is for the current running process. And the operating system has to switch that anytime it wants to switch to a different process. The process is the way by which the operating system performs time slicing on the CPU. So whatever it needs to or wherever it wants to, it can suspend one process from running, has to save the state of the process. That's another thing that we'll look at in this video, and then switch over and let another process run for a bit. So it'll switch between processes, let one process run for a few hundreds of milliseconds or thousands of milliseconds, regain control and switch over to another process. So time slice. Switch between multiple processes. Even with a single CPU, give the illusion that parallelism is happening and that all these processes are running simultaneously. So from the point of view of a process, the process abstraction provides the illusion that the program has its own private machine. So unless the process wants to explicitly communicate with other running processes, it doesn't have to know anything about other stuff that's running and using the hardware in parallel with it. It has its own virtual address space that it has complete access to, and no other process has access to it. The time slicing gives the illusion that it doesn't know when other processes are running. It has the illusion that it's just running the CPU, and it doesn't know when it gets interrupted and paused for a bit and resumes execution between one instruction and the next. So a little bit more about the address space, the virtual address space that's set up by these page tables. That will be a whole unit in this course. We'll talk in detail about how paging tables are set up and virtual memory works in the x86 operating system. So for a page table basically maps all references to addresses to an actual physical address. So there's actually a mapping that occurs. And you should understand that this mapping occurs at runtime. So the CPU is actually doing this, right? So the operating system sets up what the page table should be that's being used, but every time an address is referenced, that has to be mapped from the address space using the page table into an actual physical real address on the computer hardware. And so the virtual address, the address space of a process is laid out like this, okay? So the address space includes user memory that starts at address 0. I could be wrong, but we'll probably see later on in this course that like when you compile, like your main function, that very first instruction that starts running from main is probably the instruction that's at like address 0 or somewhere like that, right? Probably not exactly at address 0 because 0 is often used as a special address for the null pointer. But basically user data and user constants, global constants or string constants and things are going to be in the text and data area in the virtual address space for a process marked as read-only sections. Okay? Like global variables, things, there might be some others that are actually global variables that will be in sections that are read-write in like the data sections here. So some data sections could be read-only that hold constants, and some might need to be read-write, like if there's a global variable. And then on top of that, this won't have to change size. So once the exec loads the memory of the process to run, it knows how many of the sections, so how much code and data, and it'll set up a stack, a function call stack right above that can grow and shrink so that we can call functions and return from them. And again, there'll be more about this in the course. And above that, there'll be the heap. I don't know exactly how xv6 implements the heap. So traditionally, these grow down from top here, but we'll see later on this course how heap memory gets implemented for processes. We are using 64-bit architecture, so we're using a 64-bit RISC-V architecture here, but there's a couple of different standards defined. So we use the standard that only uses like 38 bits for actual addresses, which, we're not using all of the bits, so that might seem we're limiting ourselves a bit, but this is still a very large, huge address space if you calculate what that is in decimal. I should probably do that just so that you guys understand by that. So basically that means that the top of the virtual address space, since we only have 38 bits, is going to be at that address, 2 to the 38 minus 1, right? So that's the max address. This is getting a little bit into how paging works and page tables are set up, but we'll have more details about this later on. So xv6 uses 12-bit page sizes. So that means that each page actually can contain 4,096 bytes, or 2 to the 12 bytes of data on it. So, and there's two special pages at the top of memory, as is shown in this figure here. The trampoline page, and that's actually, these are both 4,096 bytes. That was a typo there. I should fix that. So this actually contains some code, and this page here is actually mapped. So both the kernel space has a map to all processes trampoline page, and every process has their own trampoline page as well. Sorry, no, that's not right. So there is one trampoline page, I believe, all processes end up mapping this part of their virtual address space to that trampoline page, wherever it's actually loaded in real physical memory. Okay? And again, we can do that using page tables, because this is just a mapping in the page table to one page in physical memory wherever we load the trampoline page. So this actually contains RISC-V assembly code, and we're going to look at this here. That's the so we're going to look at that. That's in the trampoline file. This has the code that whenever you make a system API call that you need to transition into supervisor mode, or whenever a trap occurs. Traps is another thing that we'll talk about in a later unit here. So whenever we're transitioning from user to kernel mode, we end up starting to execute this code on the trampoline page, and that will end up invoking the syscall, the system routine. And then when that system routine is done, this also finishes up to transition back from the kernel mode back out to user mode. So it goes back in and out of user supervisor mode is in the trampoline page. And I kind of talked about the process abstraction allows for time slicing. So in order to switch from one process to another, we have to save the state of the current process. What that mostly means is there's a set of registers. So every CPU has a set of general purpose registers. So for another process to run, it needs to be able to use those registers. So we first have to save the contents of those registers somewhere before we switch over to another process to do time slicing. And that's essentially what's in the trap frame here. So this saves all the data, especially those user registers, when we're about to transition and possibly run another process, and then when we're transitioning back to restart the process, these get restored from the trap frame back into the RISC-V registers. Okay? So let's jump in now and look. Actually, no, let me defer that for a second. So the XV6 maintains many pieces of state in the struct process. So this is in the proc.h, the process.header file. So it has structures in there for the page tables, for the kernel stack, run state, and other stuff like that. So actually, let's jump right in and look at the proc.h. I'm going to jump right to the process structure. So if you get into the proc.h, you'll see that there's a couple of structures defined in here. But at the bottom you'll find the one. So every process has one of these process structures that's saved in what's known as a process table that will run across here. So as is mentioned in the textbook, the state for a process is maintained in one of these process structures. So there's like a process identifier, the state the process is currently in, pointer back to the parent process. So whenever you fork process, a child is created, and you can get back or access the parent process for every child process if you need to from this pointer here. But the three things that the textbook talks about as very important state are the page table. So again, I'm going to defer most of this to when we're talking about page table and virtual memory setup. But this might not look like a pointer, but this is actually a pointer here. Oh, here's another kind of hint about using VS Code. Whenever you're using a code base here and you need to do some refactoring or understand code, that's something more than trivial code. It's really good to have your tool set up. So you should be, if you're using the VS Code setup that I give you, you should be able to like right click and go to definition or hit F12. Right, so if I need to find out where the page table type is defined, I can just hit F12. So that's over in the RISC-V header file, but it's really just a pointer to an unsigned integer. And again, we'll come back to this, but this is really just a pointer to a page in memory that's big enough to hold 512 page table entries in here. So that's the page table. Every process has its own user stack. That state is actually saved because there's a special RISC-V register that's always set to point to what the top of the current user stack is. So we don't have to save the user stack state. That gets saved on the trap frame if we're switching to another process. But every process also needs a separate kernel stack. So we'll talk about various times here. But anyway, so the separate kernel stack for each process has to be kept track of, and we're going to have be able to access the kernel stack from here on that. And then the run state. So if I just switch back to my slides real quickly, the state member variable in the process structure indicates what state the process is currently in. Unused is if that entry in the process table is currently not used by any process, it's set to unused. Initially, when a new process is forked, before it's actually ready to run, it'll be in a use state for a type. So it's allocated, but not yet completely set up, ready to run. So normally a process is either runnable, so it's waiting to run, or it's the one currently running. So, and if we have more than one CPU, we might have more than one process currently in a running state, one of them on each of the different CPUs in the system, or sleeping. If a process does some I/O, like does a read or a write or something, and needs to wait to get some data, it will be put into a sleep state until that data is available, and it can start back running again. And then finally, zombie. So when a process exits, it has to give back like a exit status back to the parent, as well as maybe do some other cleanup and things. So on initially exiting, it's put into, in Unix systems, it's put into the state called a zombie state, and it stays there until the parent process cleans up and gets the exit status, and the operating system cleans up and deallocates any memory or other resources that were allocated for the process there. So we've actually have an enumerated type. This wasn't part of the original C language, but I think it is part of the ANSI C standard that we use. It must be. It's part of the C that we're using for the XV6 here. So, these basically allow you to define, it's not a structure, these define a discrete set of possible values. So this is how the state for the process is defined. So we have these 6 possible states, and in each process entry in our process table will be in one of these 6 states here. So let me go back and talk a little bit about process switching. I mentioned some of these already, but one of the purposes of the process abstraction is to implement time sharing. So what you have to understand is that whenever we're going to share, switch to a different process, the kernel has to suspend the thread, the process that's currently running, save its state, and restore the state of another process, right? And to switch back to the process that we suspended, we have to do that thing. We have to get the save state and restore it, right? So much of that state is on the thread. So our textbook uses thread here to mean the thread of execution. Each process in XV6 has one single thread of execution associated with it. So much of that state is actually stored on the thread stack. Okay, so if I can go back here, right? So where we're currently at, so we called main function, we called function A, called function B and C. So all of that information, where we are on the function call stack, what the local variables are for each function, those are all saved in here, as well as any values for global variables and things will be down here in user text. And if any dynamic memory was allocated, that stuff will all be, that state for the process is just all accessible in the virtual address space of the process. Okay. But there is some other state that has to be saved. So I already mentioned each process has 2 stacks. It has that user stack, and the top of the stack pointer gets saved. That there's going to be one register, RISC-V register, that holds the top of the stack pointer that has to be set. So whenever we're switching to a new process, we have to set that correctly to what the address is of the stack pointer for the process we're switching into. Right, and that'll get saved on the trap frame that we talked And each process also has to have a kernel stack. We'll see more about why that is. So I did want to mention this here. So to actually switch from user mode to supervisor mode, there's a RISC-V instruction called ecall. Okay, so every CPU architecture that supports user mode, supervisor mode has a corresponding machine instruction that does this. It's meant to invoke a kernel API and to start the process of switching into supervisor mode. Okay. So I mean, it actually does it does some things for you. It saves some state and it actually switches the mode to supervisor mode. And then the operating system has to do some other things once it's in supervisor mode to safely save the rest of the state and invoke the kernel system call that was being asked to be invoked here. So yeah, to do a process switch, after the ecall does its thing, we'll see this is the beginning of the entry assembly code here. We have to. So the ecall basically switches to supervisor. This is the stuff that the ecall instruction actually does. It changes to supervisor mode. It changes the program counter to a kernel-defined entry point, right? So it is actually changing the program counter itself so that we start executing from a known location. Essentially, that'll start executing from the trap frame. So as we'll see here, to do the reverse of this, an S return instruction has to happen. So this is what causes the switch back of the user mode, of the supervisor mode back into user mode here. And the result of this should be that it should end up resuming executing the instruction just immediately after the ecall system call instruction. All right. Okay, so with that, we're going to spend a little bit of time looking at the boot process for XV6. But by doing this, this will be able to give you a bit of an understanding of some of the things we're just discussing, including how processes work. Once we get down here and look at how the initial user process called init is created. So Unix operating systems pretty much they all work this way. So there is one at the end of the boot process. There's one special user process called init that's created that usually runs a shell or something like that. Okay? So let's start. So the hardware bootloader will be set up to copy the kernel into memory at a specified address. Okay, so the kernel is actually going to be copied into memory, and it knows that it'll be copied into memory starting at this address here, hex 80000000. Okay, so as the textbook mentions, the reason why it places it here instead of address 0 is the I/O device mapping for the RISC-V architecture is actually mapped to the addresses 0 up to 7 FFF, FFFF. Okay, so that's kind of reserved for hardware I/O mapping stuff. So at this point, after the bootloader does its thing, we will jump to the entry point. Okay, so what we mean by jumping to is the program counter gets set to this address, so whatever instruction is at this address will get fetched, and we'll start doing fetch execute from this instruction in memory. All right, so at this point we're still in machine mode. So remember, there's actually 3 modes that RISC-V implements: supervisor user mode, but also this machine mode. So in machine mode, that's the initial mode at boot. Paging hardware, so virtual memory is completely turned off. So all address references will just be treated as actual real physical addresses. Okay. So what happens, I'm going to jump to this code here. This basically sets up a stack so we can start running C code. All right. So we actually have to have a stack if we want to start calling C functions that might call other functions so they can push and pop things off the stack. So once it sets up, it basically just loads the stack pointer into the stack pointer register. So we'll see that's the register that has to hold the location of where the stack is that should be being used whenever instructions are called that invoke or return from a procedure. Okay? And then it calls start. Okay, so let's look at this code here. So let's look at the entry.s file here. So it's relatively small, and like we said, this is, this symbol is going to actually end up at this address once the bootloader is stopped. Remember, I'll show this here because I'm actually going to run and step through this code. But when QEMU is invoked, one of the parameters is called kernel, right? So this is basically simulating the boot process of real hardware. So that kernel image that you get is just directly loaded at that address. The program counter is set, and we'll start fetching and executing at that address here, which means we start fetching and executing these instructions. Okay, so this just does exactly what we discussed here. This is really just setting up a stack. All right, so it loads the register, and this is RISC-V assembly. And like I said, I think this is RISC-V assembly is fairly easy to read, a lot easier than Intel or ARM for the most part. So a lot of this is, along with the comments given, is usually relatively understandable, right? So all we're doing is loading the stack pointer here with the stack 0. This is mentioned in the comment here and in our textbook. The stack 0, if you want to find it, fortunately, not everything can you jump to definition. It depends. But yeah, it's in the start.c. So if you look in start.c, we're going to go to there next anyway. You'll find that there is a declaration of the stack 0 in here. Yeah, right here, right? So yeah, it looks a little bit ugly because it has some other stuff in there, but this is basically just an array of characters, an array of bytes. Although there's one page. Remember, our page size is 4096, so there's enough. The XP6 uses very simple stack, so it assumes that a stack will never be more than one page in size, which is pretty limiting to how deep your function call stack can end up going. But basically, there's going to be one page for each CPU. So if I have 2 CPUs, there's actually going to be enough for 2 pages on stack 0 here. Going back here, so I don't think this is discussed in the textbook, but basically, to support multiple CPUs, it actually sets the stack pointer. So all this code here is, like is mentioned in the this comment here, is it's just setting the stack pointer to one of those multiple pages, depending on however many hardware threads, basically how many CPUs are on there. Right? So if I'm on thread 0, I want to be at the bottom. So these stacks grow towards smaller addresses. So I want to be at the largest address, kind of at the bottom, so I could grow back towards the top, or however which way you think of it. So if I'm at 0, I want to just be 1 times 4096. If I'm on thread 1, I want to start my stack pointer at 2 times 4096 to be at the base of the second page that's used for the stack there. So these instructions here basically, so this loads 4096 into A0. This loads my hardware thread ID into A1. This adds 1 to it. So A1 now has my hardware thread ID plus 1 after the add, and then this multiplies the A1 times the A0. So basically it's doing this multiplication there. And then this does the add, to add that to whatever the offset is for stack 0. And the result of that ends up back in the stack pointer, okay? So again, the result of all this is that the stack pointer register is set up to point to an appropriate page on this stack, wherever this gets allocated in real memory here, so that we can start calling C function calls here. Let's compile it and run it in the debug mode so we can step through this. So we'll run it with only a single CPU. What was it? GDB. Notice I wanted to point out here, these options, so you might understand this more. So when we built the kernel, there's a actual executable file in the ELF 64 format, right? So this is actually being loaded by the bootloader at that particular address, the entry point that we talked about. Okay, so now we should be able to run our GUI here, or run in the text user interface mode. We'll set a breakpoint at entry. We can step through these here. So, for example, let's look at the registers at this point, info registers. So you can see most of these are general purpose registers. Let's just find the program counter. And the stack pointer might have gone by. So, I mean, of course, the program counter shouldn't be a surprise since we said that. So we're currently at the entry point here. The stack pointer is currently at 0. Okay, so if I step over this, and look at it now, I way to print out the stack pointer. So the stack pointer has the location of stack 0, and then these will do the other manipulation. So since I started with just a single CPU, it should just add 4096 to that, right? So we'll see if that in fact happens. So if I just next, and we look at our stack pointer now, it's hopefully that stack plus 4096. Okay. So we could have looked at what the heart ID was as well. It should be 0 in this case. Oh yeah, it's that there. So I don't know if I have that symbol or not. I guess not. But anyway, actually that should be 0 here since we've only got one CPU. Okay, so we're ready to jump into the start here. So we're still actually in machine mode. So when we look at the start code here, I mean, this is our first actual compiled C code. So we're actually going to be running C code here. This does some setup that can only be done in machine mode, and then it switches to supervisor mode. So all the stuff that's happening in the start.c here is really doing stuff that needs to be done in machine mode before we can actually get into user supervisor, switching between user and supervisor mode for the rest of the time in the hardware. Then a setup in order to correctly switch into supervisor mode for the first time. So notice that call is the basic machine instruction that allows for procedure calls and returns. And this is what C code, whenever you do a function call of a function in C, is going to end up being a call instruction in RISC-V here. Right? And actually, it's not really supposed to ever return from start. So there's kind of, the spin is just a jump. So it would just endlessly spin forever if it ever end up returning from this call for some reason. So let's set a breakpoint at start and just continue on there so we can actually just step through my start. So instead of using my editor, I'll just go ahead and use the GNU debugger to look at the code as we're stepping through it. So we're in that special machine mode still here, and we're using the stack 0 that we set the stack pointer to. Okay, so start performs some setup that can only be done in machine mode. So most crucially, it's setting up the clock chip to generate interrupts. So yeah, actually I'm going to jump back to the editor here. So this function, if you look at it or go to an F12, you'll see it's doing basically some functions that are actually just calling RISC-V assembly. So these manipulations are enabling the timer interrupts, and I think that this sets one to happen after a million microseconds or something like that. So basically, the timer interrupts allow for the operating system to regain control. So even if like a program's in an infinite loop or is just doing for a long time, the operating system will regain control, so it can do basically time slicing. If it can switch to another process and let it run for a bit. Right. So these timer interrupts are crucial to be set up. Okay. This is timer init is in the start.c file at the bottom. But so besides that, everything else above that is really setting up so that when we invoke mReturn, we'll actually switch into supervisor mode correctly, and we will basically be in supervisor mode and be in the main function. Okay, so basically, for example, we're setting this MEPC, this program counter. That is the thing that gets reloaded into the actual program counter when the mReturn happens. So we set that to be the address of main, so that on the mReturn invocation, we start executing from main. We still have paging turned off. We're not going to turn that on until we actually create a process and start running in user mode with a process that has a page table. And some other setup to get interrupts and exceptions to go to the correct place. Okay, so let's just go back and step through this. So notice that we're on the start now, right? So the location of start is at this location, program counter 800058 here. So we are setting the previous privilege mode to supervisor, so that when we do the mReturn, we will switch into supervisor mode for the first time by doing these instructions. Oops, I meant to step over these here. And we're setting this mException program counter so that when the mReturn happens, it'll restore and we'll start fetching and executing from main in supervisor mode at that point. Disabling paging and doing some other stuff. So I will just set a breakpoint here. We set up the timer interrupts, and we're going to do the mReturn here. So let's set a break on main. So that should be our function in main.c here, which is at that location of the program. And I should be able to continue on, and we'll start executing from this point. All right. So main is basically initializing a bunch of stuff, and then at the end it will actually create the first user process. Okay, so if you look at the details here, a lot of this stuff only needs to be initialized once. So all the code in here only happens on the CPU with an ID of 0, right? With a heart ID of 0. So some things have to be done on all CPUs. That's what all CPUs. We have to turn on the paging, install the kernel trap vectors, and do this click device interrupt. So you'll see that those are done here and also here. So all those happen in both places. But some things like initializing the console, setting up the inode tables, and some other stuff, and creating the first user process should only happen once. It shouldn't happen multiple times. There should only be a single user process. So we just step through this. So notice this is where we get the output message about the kernel's booting. Right. So if I do next here, we should be running for CPU 0. We only have one CPU the way we started it up, so we should be doing this stuff here, right? So notice if I go back and look, nothing has been output from when we invoked the quick emulator. So we're about ready to actually do our first output here. I mean, if you modified this and recompiled, you would get different message here. Be something you could try just to see that it's actually running the stuff. So as soon as I do this, I should see that we've got our message. So that print K is actually causing something to be displayed out on the console that was set up here, right? So these are doing stuff before we set up file descriptors and stuff like that. But we do have the console initted. So print K allows us to print stuff out on our console kind of in a raw mode here. So at the end of all this initialization, we will call the userinit. So I'll just go get down to the userinit. So this is going to create the actual first user process here. So let me see if I can step into this successfully. So remember, next is supposed to step over, but S or step is supposed to step into a function when you're using the debugger here. I was doing it wrong in some parts of this video here. So if we step in, we should be in the userinit, which is in the proc.c file. So let me switch back to the code here. I might stop stepping through here and let's just discuss. So when we're in userinit, this is going to create the first process that's meant to be running in user mode. Okay? So notice the first thing it does is call alloc process, and then it sets whatever process is returned. It expects a process structure to be returned from allocate process. And it keeps track of that initial process with a special variable called init proc. But if we look at allocate process, so this gives you the idea when you look at the allocate process of how the beginnings of how process management works on XV6 here, right? So there's this, it's really a table. I think of it as the process table that's really searched through here, right? So the loop here is going to start at the first entry in this table and check them one by one. It's using pointer arithmetic. So the first time it'll be whatever the first entry is in the table, the second time the second entry, up to the number of processes that are defined. So in proc is defined as 64. So only 64 processes can actually be created at most in this. And proc is defined at the top of proc.c, right? So this just looks like a regular declaration of an array of proc structures. I maybe shouldn't have skipped past too quickly, all the stuff that's initializing. So, I forgot to mention that one of the things that gets called is that this proc init to initialize the process table gets called here. So the process init process table initialization is just a little bit above the allocate process. So you'll see that we'll have to talk about with locking and unlocking, but these are basically concurrency mechanisms. If you're familiar with what we mean by those, I'll ignore those mostly. But basically, this loop is just setting every process to be into that unused state, and it's creating a kernel stack. So every process is going to have a kernel stack already pointed to by this. But that's the only two things that are set in the initialized process table, right? So if we go back to the alloc process, basically it's searching through here for the first process that's in an unused state. And as soon as it finds an entry in the process table that's unused, it does this code here. Okay? So this just allocates a process identifier, so this should be 1 initially. Right? So if you look at this, the next PID is a variable that just starts off as 1. So the very first process identifier, first time we call that alloc PID, we should get a process identifier of 1 return. That just keeps incrementing So even though we only have room for 64 processes, process IDs aren't really reused unless we were to go create so many processes we wrap around. That is something that you might be able to exploit that to cause a bug, although it'd be tough to do because the next PIDs are just 64-bit integer, so it'd be a really huge number of processes you have to create before you wrap that around. So here's some of the kind of the important stuff that gets set up. So each time a process is allocated, including the special init process that we're working on right now, we allocate a process identifier. We allocate a trap frame page. Okay, so the trampoline page is saved and is set up in the process table, but the trap frame page is not. Right. So this actually allocates something in real physical memory. And we just remember that. So we're going to set that up to be the trap frame that's used in the address space for the process that we're creating. And then we create the actual page table by calling the process page table. And I'll save the details of this so we're going to talk about page tables. So at the end of the alloc process, it's going to return the process that was allocated. It sets up a few more things. So basically what it's setting up here is that when this process is, remember this is a new process that's being created here for the alloc process. So it sets it up so that when this process is selected by the scheduler to start running, remember fork is how a parent process creates a new child process. So normally we set this up so that when we start running this process, this is going to be the location where the program counter will be set to start executing from when we select this process to run. And also, at that point, fork is a system call. We'll be in supervisor mode, so the stack is going to be set up to be pointing to basically the top of the kernel stack, right, which is empty initially for every process when we create it. And then we just return the process structure that we just set up and allocated here from the result of calling alloc. So remember, we had gone into userinit from main here, and this is some special code that sets up the first user process, right? So remember, we had called alloc process to allocate the init process. So now we basically we're ready. The process is ready to be runnable, so it's put into a runnable state. We set the current working directory for the init process to be the root of the file system in this case, and we're done there. So you might ask what happens at that point. So when userinit returns, notice the last thing that happens in main is it calls the scheduler. Okay, so this will be another unit we'll talk about. We'll talk about process scheduling, but this basically, if nothing is currently running on a CPU, the scheduler will pick a process that's in the runnable state and start it running. And also remember, when we looked at the alloc process, that it set it up, the initial process that we created, it set it up. Find it instead of scrolling through this stuff, another hint I usually do like to make use of the outline. So alloc process, not alloc PID, alloc process set it up so that the new process, when it was first scheduled, will start executing in the fork return, basically. So this is discussed in the textbook here. So normally, to create a new process, an exec would have to be called. There's a special case though in fork return that detects that that the init process is being returned from here. So let's look at the fork return. So the fork return is still in the proc.c file in there somewhere. There's nothing to actually fork a new child process for the init process. So that's why basically this is a special case in fork return. So you don't have to exactly understand the details, but basically if this is the first process, it's going to call k. So normally when you call exec, it ends up calling kexec, and you give it the image of the new code to be loaded. So this, as a special case, will load the code. So this is where the code of the init process, which is just hard-coded to be somewhere in the root directory of the file system, gets loaded into memory here, right? So this should set it up. And this will, I'll go into this later here. So if you look at the kexec, this will set it up to, once it loads this, to set the program counter on return back into user space to be calling, the main function code, basically. The image that we just loaded here. Okay, so that's it for this video. A little bit longer than I usually wanted to go, but there's some important stuff in here. We've taken you up to the point now where we can actually look at the details of the page table creation setup. Also, we need to explore more like that trampoline page, how that works in order to switch from user mode to kernel mode and back. So in summary, what you should have taken away from this video is that the unit of isolation in Unix-like operating systems is the process abstraction. So having support in the hardware for a user supervisor mode flag and something like a page table for setting up virtual memory is essential to implement the process abstraction, which is one of the basic functions of this abstraction is to provide isolation. So to provide security, to allow multiple things to be running and using the system resources and not be able to interfere with one another, right? So that address space, that virtual address space, has the user code and data. We took you right up to the beginning of that. So that special exec call that's loading the init image is how the code and data for the initial process gets loaded into the virtual address, the page table address space that was created just before, just at the end of the outlet process that we looked at. Okay? So keep in mind, we'll come back to these. There's these special trampoline and trap frames that are mapped both to user and kernel space. The trampoline page has code that's used to transition in and out. So when we talk about traps and system calls, we will actually go through this code here. And the trap frame, we'll also look at how these work. So, but that is the reason why these are talked about here is part of doing time slicing to switch between processes is we have to save the state of the process before we switch to another one. So that state, especially the registers, basically gets saved in the trap frame here. But we did look at a lot of the details of the process structure and the process table. These are all defined in the proc.h file here. All of that infrastructure is needed to support process switching. So process switching is done by the kernel, which suspends the currently run process, saves the state, and restores the state of another process to run. There's 6 basic states that xv6 has. So it's either runnable, it's currently running, it might be zombie, or a couple of other states. Sleeping, if it's waiting on some IOs, it's a sleeping state. Another important thing that we're going to see in the next chapter is the process, the page table for the process that holds the page table, which defines the virtual address space that each process can access. All right, so that's it for this video. As usual, I hope you find these things useful. Let me know if you have feedback or comments. There should be links in the video description to any of the resources that we used. And I will see you in our next video.